Okay, take it away, Rachel.
Hello, everyone. Welcome to the June edition of the Audio Programmer Meetup. Thanks so much for coming to join us today. I co-host this meetup on the second Tuesday of every month with my co-host, Joshua Hodge. How are you doing tonight, Josh?
I'm great. How's it going, Rachel?
I'm all good, thank you.
Yeah, so we do have an exciting Audio Programmer Meetup for you today. Today we got the UK connection because everybody here is in the UK, aside from myself. So we have Tom, who's dialing in from Shropshire, up near Wales. He's the director of JUCE. We have, of course, my co-host, Rachel, who's dialing in from London town. And we have Geraint, who is with us from Cambridge. So before we get started, just wanted to give a big thanks to our sponsors, JUCE, Sonics, and Focusrite for sponsoring the Audio Programmer Meetup. Without them, this meetup wouldn't be possible, and just wanted to thank them for their support. And as always, you can join our audio programmer community to continue this discussion. And you can join that on theaudioprogrammer.com/community. And with that, I will hand the mic back to Rachel to introduce our first speaker.
Perfect, thank you. So tonight our first speaker is Geraint Luff. He's a DSP engineer, musician, and mathematician from Signalsmith Audio. And tonight he's going to be talking to us about designing a straightforward limiter. Take it away.
Hi. Yeah, so I'll just share my screen. I can get that to work. Cool. Can people see that?
Yep, all good.
Excellent. Right, so today I'm going to go through designing a limiter, and by designing I mean it's a bit of a thought process, sort of full disclosure. This is not something I researched a lot before I wrote one. So I needed to write a limiter and had a sort of first you make the requirements, then you figure out how to solve the requirements. And so we're just going to walk through that process. I have no inner knowledge of how any specific commercial limiter is made, but this is a hopefully nice, simple design, which people can get going with if you're curious about. So here's the challenge. We have some kind of signal, and the waveform goes outside the range that we want. So here is our sound. So you can hear that there we've got a mixture of some smooth textures and then some transient drums kicking in. So this is a sort of classic problem for a limiter, because you want to keep the drums tamed, bring them in, bring the peaks down, but without ruining too much the overall sound. So yeah, how do we do this? The obvious thing to do is we want to change the gain over time. So if this is our waveform, then while the waveform is inside the allowed limits that we have decided we want, we can just pass it straight through with gain 0 dB. And then when it pokes outside these regions, we scale it down just enough so that it gets brought back inside the limits. So here's some C++ code to do that. Yeah, we calculate a gain value, which is, is it outside the limit? And then if so, we bring it back in. Otherwise, we return 1. And if you really want to be nice and concise, here's a sweet little short one-liner for that. And yeah, this is what the gain graph looks like. So you can see that where there were sort of these peaks in the input audio, the gain has dipped down. So let's have a listen to that. You see, what we've done here is we've accidentally created a hard clipper, because whenever the signal goes outside the allowed range, we just bring it exactly back to the limit. And so these fast changing gains that we saw here end up modulating the signal really fast as it sort of, pops up and down outside the limits, and it sounds a bit awful. So what we really want to do is this is the maximum gain that we're allowed to apply to our signal. So we want a nice smooth gain signal that stays safely below this calculation that we started with. So these are the requirements that we've now laid out. We want a smooth curve, and we've got our sort of very awful clipper style gain, and the curve has to stay below those gain values that we just calculated. So there is a neat way to solve this problem. It comes in 2 steps. The first is a moving minimum. So the red dotted line here is the minimum gain in the last however long you choose, 20 milliseconds or so. So you can see already that this is a nice, it's not as spiky. And then we're not going to listen to that. But the next step we're going to do is we're going to get rid of the spikiness. Oh, no, we're not. We're going to look at some example code. Sorry. Yeah, so let's assume you have some kind of moving maximum. I'll talk a bit later about how you might try and do that. But yeah, you know how long you want your holding period to be. And when you get a sample in, you calculate a gain, which is this calculation we had before. And then to turn a moving maximum into a moving minimum, you invert the input, and then you invert the output. So this gives you the graph that you have here. And the next stage is we're going to smooth out this moving minimum. So you've got these sharp jumps here at the beginning and the end. If you take a finite length, any kind of average, weighted average across this period, then hopefully you can see that if the average is limited to this range here, then the weighted average will be also below that peak. So we can see this in this graph here. We've added the green dashed line for the smoothed version of our moving minimum. And so this is the way that we've chosen to solve this today. But the general principle of you start with the most obvious thing, which is, okay, just apply a gain to bring it back into range. And then you sort of deal with that problem and you're like, okay, well, let's try smoothing it, but smoothing it's not enough. You try whatever tools you have to hand. And let's look at the code for what we've just written. No, let's look at the flow for what we've written here. Wait, hang on. Where's this? So sorry. As you can see, the green dashed line is slightly behind the blue peaks. So we have a nice smooth gain curve, and it's just whatever it is, 20 milliseconds or so behind the peak you want to get. So what we have is we have two paths in our flow, and we do our maximum gain calculation. That's our awful clipper. We do our moving minimum, and then we do our smoothing. And this is our dashed green output here. And then we correspondingly, interesting. We correspondingly delay the actual audio signal to bring the peaks in line with the reduced gain. Here is how you might do that in code. So these are just setting up the ingredients. You say what your limit is, you say how long your attack should be, And then we use our peak hold and then any kind of smoother here. I'll talk a bit later about like what types of smoother there can be. The simplest would just be a box filter, right? So a moving average that just takes the average of the last 20 milliseconds. But any finite smoother, finite filter will work here. And then our delay to delay the input signal. We configure with the sample rate and we convert our millisecond specifications into samples, and we pass that to the smoother and the moving minimum and the delay. And then we have our gain calculation. We have our awful clipping gain. We have our moving minimum, and then we pass it through whatever smoothing filter we have to hand. I'm using some examples from my DSP library here, but like hopefully there should be similar utilities around in other frameworks. And yeah, so here we should report our latency, which is whatever our length was, 20 milliseconds or so. And yeah, we take our input sample, apply the gain to get the gain, and then we read a delayed signal and apply that gain. Yeah, so here's what sort of that output looks like. And let's have a listen. So that's a lot better than our first attempt. We've had a smoother gain envelope, and but we stayed strictly below this clipping curve, which means that our output is also stays within the bounds. This is actually a completely functional limiter. This works. I'll play that again. So this only has one dial at the moment. Well, it's got the threshold and the smoothing time. And if you look at the curve that the gain takes when you have a peak, this is a diagram of what happens if you have a big peak at some time 0. The maximum gain, our clipper gain, is this red dashed one, and it will have a massive dip in it because for that sample, we need to reduce the gain a lot. We did a peak hold, which isn't on this diagram, but you can imagine that sort of just extends this line out into a sort of square. And then we've done our whatever smoothing we've used, but it's symmetrical. And it might be that we want our attack to be short and then to take slightly longer to come back in. So this can be done really easily. This is our flow, and it's exactly the same as before, except we've just added a release element here. Now, the simplest one to add is an exponential release. So this is our minimum hold, moving minimum signal is the blue one here. And then our release curve that we're creating is going to be this exponential one. So when it decreases instantly. When it increases slowly. And I'll zoom out so you can see the code. Yeah, so you calculate some kind of averaging value for your exponential, and then every time you have an input sample, you move towards it slowly, but if it turns out that you're decreasing, then you move down instantly. So this is how you can produce this kind of release curve, and it's hopefully reasonably straightforward. So this would just be like a first order sort of one pole smoothing filter, except we've added this instant move downwards. And in the flow here, we've put the release before the smoothing. We've put it between two elements. You can have a play around. Like if you put it here, then it sort of takes any sharp corners off the envelope. So the envelope is always smooth. But yeah, try a few different things. Like this isn't coming from a place of very detailed wisdom. This is just something that works. The other thing you might want is hold times. That's pretty common. If you've got a lot of peaks in quick succession, you might want to still have a fast attack, but to not actually start your release for a bit. This is, again, really easy to add to our flow because you just increase your moving minimum by a bit more. So previously, our moving minimum was exactly the same as the smoothing length, and now you just hold on a bit longer. And if you look at, this is the gain response with both of those things added. So this is our dip in the maximum gain because of the loud signal we've had at time 0. The attack length here has smoothed the attack. Then we can see that it holds on for a bit longer. And then we have our release curve, which was exponential, but as I said, we put it before the smoothing, which means the start of this release curve is also nice and smooth. Yeah, so I don't know if you can actually hear the difference between that and the previous one over Zoom, but we've definitely got more controls, and audio people love dials, right? Add more of them. Yeah, so that's a sort of, this works, and let's look at the example code that you might use to write this. So we've got our 4 parameters here: the threshold, attack, hold, and release. We've got the same things that we had before with our sort of single time control, except we've now also got this exponential release, which is exactly the class that we saw before. Zoom out. Yeah, after a while, this code stops becoming pretty, but basically we are still converting milliseconds to samples just repeatedly. We're setting up our exponential releases. We're setting our peak hold to be not just attack samples, but attack and hold. So our moving minimum will extend beyond what we originally needed. And then this is, again, exactly the same, except between our moving minimum and our smoother, we've got our release envelope. And then, yeah, exactly the same as before. We've got an input sample, calculate the gain, read a delayed audio sample to compensate for the latency of the smoothing, and then we go and apply it. So I've just made a bunch of off-the-cuff choices about how we implement which release curves we use, how you do attacks. Like, I haven't explained any of the details of what makes a different one different, and I'm not going to. This kind of when you have all these different options that you could take. Some of it is a question of judgment and opinion. Personally, I like to find a good metric, some numerical thing you can measure, and then you can test your implementation against that and then optimize it and find some best solution. But what you choose for that is also up to you. But yeah, you start with anything, and then you can start getting making more subtle choices. But I'm just going to sketch out a couple of things that you might want to do. So there's alternate ways you could release. Instead of exponential, you could just increase the gain at a fixed ratio. There's quite a funky one where the gain increases back to 1 at a fixed rate. So the release always takes the same amount of time. This is quite fun. If you cascade multiple exponential release curves, this is our blue one. where, you know, we've had some instant reduction and then later it's decaying back up to 1. If you cascade them together, then you get softer and softer starts to your release curves. You can also cascade that sort of fixed length one. I'm not going to go into the detail of how the fixed length one works here, but another thing you probably want to consider for a limiter is intersample peaks. So we have so far just concerned ourselves with making sure that each individual sample is within the output range that we want. But when those signals go to the DAC, or they get encoded into a WAV file, maybe there are errors or there's sample rate conversion or something, then you can end up with these peaks that pop outside the range, even though the individual input samples are within it. Again, this isn't actually too difficult to incorporate once you know what that value is. So the thing you basically would want to do to tackle this is, instead of for each sample calculating just the gain for that sample, you might want to oversample or upsample, or in some other ways interpolate to get some of these intermediate values, and then just take the minimum gain and then assign it to that sample, and then all the rest of the smoothing and everything else it can be the same. Yeah, there's a few different things to try. We worked at the moment with everything being just dealing with amplitude, but quite often the attacks and releases of, you know, compressors and stuff will work in decibel space. So we could do that here. Like, all you have to do that is you take your maximum gain from your sort of clipping gain, and then you convert it to dB, and then you do all the same things that you did before. And then before you actually apply it to your signal, you convert back from dB. So that's just another thing that you could do. I talked about how you might calculate a moving minimum. That's a whole other thing. If you have an off-the-shelf one, use it. But if you're rolling your own and you don't fancy reading my blog post about it, then another thing you can do is you can just, to save a bit of CPU, because recalculating the whole minimum every sample would be horrendously slow, but you can kind of chop it up into smaller regions, and you can keep updating this like smaller one at the front that keeps growing, but these other chunks that you've previously calculated, you already know the minimum for that, and you just store it. And then at the end, you can just do whatever it is, 10 minimums for the comparison. It's not the most efficient, and you also get the problem that, like, you can't drop this off gradually. So maybe sometimes your minimum is slightly longer than you need. But again, it works and it's fine, and you can place limits on exactly how bad it is by how finely you chop it up. The finite smoothing. So we've had our done our peak, or sort of moving minimum, and then we had to have our smoothing, and it had to be finite because we knew that our moving minimum was going to be less than, our gain was going to be less than the what we needed, but only for a fixed amount of time. So we needed to have a smoothing function which was 0 outside that, so that all the averaging that we took was from within that region where we knew it was less than. I said we needed to, but like, what happens if you don't? If you don't want to do like an FIR filter, you can cascade a few other filters. You can cascade a bunch of one poles, and it will be almost 0 by the end of the period you need. And that means you'll be almost correct, and you'll be just over the limit occasionally, and you can actually clip your output at that point. Yeah, Dario on the audio programmer Discord and I have had some fantastic discussions about this, and yeah, I've got a link to his paper from the blog post because he presented it at the Faust conference because it's interesting. We both started from the same first principles situation and ended up with different enough solutions that we had some great chats about it. And there's a bunch of other things you could consider. Adaptive release or splitting it into bands is always kind of appealing because that's what you do for compressors and stuff, and that's slightly more transparent. But it gets sticky because if you split it into bands and then some of the bands like actually go opposite directions after you've done the band split, then change the gain of one, it could make it worse. My point is this is a basic design. There's a lot of places you can take it. But what we've made actually works. So we start with our hard clipping kind of gain. We've specified our attack time as the smoothing period, hold time, which is how much extra peak hold, and then release time. And this is a very, very simple design. And yeah, it sounds pretty good. Actually, I'm going to load up Reaper now, and I can show you some things. Show you it working on a live track. So hopefully you can see and hear this. So what we have here is the green spiky signal is this clipping gain that we calculated in our flow. And then we've got this, this is actually just using a box filter. So a rectangular moving average, which can be done very cheaply after that peak hold. So for this peak, I'll have a peak hold, and then there'll be a moving average after that, which means that the average for that period is always going to be below the peak you need. And then we sort of shift it back in time with latency. If you want, instead of using single box filter, you could use two. If I can make this slide work. And you can see that this is sort of, when you have a single peak, you get these kind of straight line looking segments. Whereas you can see that the eventual gain curve we produce is actually nice and smooth. So yeah, that's pretty much it. That's the talk. Are there any questions?
Thanks so much, Geraint. That was really awesome. I'm going to give the live chat a couple minutes to come up with some more questions. I had a couple questions. One question I had was going back to the part where you said, maybe I heard this wrong, but you said that sometimes reconstructing a continuous signal from a discrete signal, you can get, even though the values in the discrete signal are below the limit, below the limiter, below the threshold, that they can still produce values that are above the allowed range. Yeah. So can you explain that a little bit further?
Yeah. So when we have an audio signal, it is sampled. So we know its value at a particular moment in time, and then a bit later. But in order to send it down the wires to speakers or various other things, we have to add more values in between. And this upsampling, generally, you can kind of think of it as being like a low pass. And so when you create a smooth curve from these points, like it'll, how do I explain this? This bit up here is going to be some amount of this and some amount of this, but it's also going to subtract some of the other ones. So it's not just the kind of positive only smoothing low pass stuff that we had for filtering the gain envelope, this is the ideal form as a sync filter, but whatever filter you use, it's going to have ripples in the impulse response. And so you could end up with a situation where you add a positive one and then subtract a negative one, so that it ends up catapulting the output slightly outside. I don't know anything up.
Got it. Another question that I wanted to ask was, you had talked a little bit about what gives a limiter character. So would you say that it's mainly to the way that the filters are constructed to give it its appropriate attack and release times? Or would you say that there are more, that it could be more, potentially more complicated than that? What is it that gives a limiter when people say that it's, let's say, an analog style limiter? What would that entail?
Yeah, so what we've created here is it's a look ahead limiter, meaning it uses latency, and it's a brick wall limiter, meaning that it exactly limits the output. But our goal mostly was to be linear. So we didn't want that kind of fast changing gain that originally caused our very clipping sound. But actually analog limiters or various other things, like, because you're taking down the peaks, you can sometimes lose the edge. So this is kind of a very vanilla approach, and a lot of like a good limiter that you might sort of pay a lot for, or you want it in hardware or that kind of thing. There'll be some extra magic, again, as I sort of said about start with the thing and you find a problem. Like, you get this far and then you go, hang on, my bass drum doesn't go like it used to. So if you maybe undershoot your limiting, as I talked about with that, the not quite finite limiting, then maybe this this curve here wouldn't quite reach the peak that it needed to, and so you, for that tiny instant, get a bit of clipping, and that kind of thing is quite common in more analog setups, because you don't have this sort of perfect digital look ahead, and it adds character. It brings back some of the sharp impact that you lost by reducing the gain. That's not the only way you can try and do that. You could do some transient processing explicitly to try and get that kind of thing. But the character is sort of lots of small choices, the exact curves, the exact release curves, and then obviously anything excitingly nonlinear on top of that.
Got it. And then the slides and the code you have on your website, right? Would you like to shout that out? And I'll also put it in the video description as well.
Yeah, so let's see. I should have loaded this up. That would be very smart. I did not. Yeah, but it's currently my sort of latest one. No, that's not the right one. Yeah, there we are. So this is the exact same presentation, but in blog post form. It's not exactly the same, but yeah, and you've got the example code here. And I'll also put this up on GitHub in case that's useful for anyone.
Awesome. So it's signalsmith-audio.co.uk. I'll put that in the chat as well for people, and I will put that in the video description later on. We have two more questions. One question, wouldn't it be better to use a ballistics filter or an envelope follower using absolute value or windowed square root mean? That is kind of what you did, though, but you did it more from scratch. Am I right in saying that?
So the ballistics filter is, if I am understanding what that's referencing, I think that's infinite impulse response. I don't think that's finite, unless that's the one. Maybe that looks more like this kind of one of these two. Yeah, like, why not? I think the question with the RMS is, I need to find a way to turn off the audio examples. Yeah, so in this architecture, the absolute value is here, And then our smoothing is done here. Like RMS is more something you'd use for a compressor. So you could make a compressor on a very similar design, where instead of this absolute value and then moving minimum, you would do a squared or absolute value and then filter that. And that's your energy metric. And then you, again, calculate your instantaneous gain that you want and smooth out your gain changes and add a release curve. Yeah, I don't think you tend to get RMSs and limiters. That's more of a compressor kind of thing.
Got it. But the only difference between a compressor and a limiter is just the ratio, right? Like, isn't a limiter just a compressor with a infinite ratio?
A compressor works on a short-term energy metric, which is more like the kind of perceptual loudness. There's no guarantee that like that perceptual loudness implies a limited waveform. So a limiter, you have like a very strict requirement of what samples you want, whereas a compressor, your requirement is more about how loud it sounds. And so your gain calculation is based on something slightly different. Here we're using kind of instantaneous sample by sample gains. And then for a compressor, you might want, your short term, like 5 milliseconds or 10 or whatever it is of audio, and then calculate a gain according to that. But if you just crank a compressor up with 100-to-1 ratio, it won't inherently produce a limiter.
Got it. Okay, great. There's another question from Jas asking, is there a way that you could simply turn this into an expander?
So expanders are more similar to compressors, but the basic principle of you get some metric, whether it's your sort of moving minimum peak or a short time RMS, and then you map that gain. So you just do exactly the same things as you would for a compressor, but instead of if it's above this threshold, then scale the dB down. You have if it's below this threshold, scale down. I think I would use a more compressor style metric like RMS rather than basing it on waveform peaks for an expander.
Got it.
But yeah, a lot of these dynamic processes you can come to them with the same kind of attitude.
Awesome. Great. Thank you so much, Geraint. That was really awesome. And as I said before, we will be sure to put the website in the description below for people who want to look at the code and the explanation a little bit further. So thank you very much. And with no further delay, we'll move into another talk about DSP. So this is a great meetup for DSP aficionados. And this talk is another edition of DSP Corner. So as you may or may not know, Rachel Locke, my co-host, has been giving monthly discussions on fundamental digital signal processing concepts. So if you want to make limiters, make compressors, delays, these are some of the fundamental techniques that you may want to learn about and know about. And Rachel is a recent graduate of the University of West London with a master's degree. I'm not going to say it's in digital signal processing. It's in something slightly related to that. It's like music. It's in something, the technical name is something very misleading.
It's digital audio engineering.
Digital audio engineering.
Which is quite misleading, yes.
Yes. But she studied digital signal processing, and she's been nice enough to give us these monthly presentations to help other people like myself learn the fundamentals. And today she's going to talk about another fundamental, which is complex numbers. And I will let you take it away from here, Rachel. Take it away.
Perfect. Let me just see if I can share this. One moment. Are we seeing the slides?
Yep, you're all good.
Perfect. Let me just slideshow it up. I feel like I say this at every DSP corner, but I'm getting a bit of a scratchy throat, so I promise I'm not always ill. So please bear with me if I need to take a drink of water or if it gets a bit husky. Thanks for the introduction, Josh. Yep, this is the third episode of DSP Corner. And I would say that Josh mentioned DSP aficionados, but perhaps this segment is a bit more for your DSP beginners or intermediates. Maybe there'll be something if you're already quite deep into DSP, but I'm not quite sure. But you might still enjoy it, and nice to have a primer and a recap. Today we're going to talk about complex numbers, because complex numbers, they're not always like an immediately obvious area that you look into when you look into signals, but just because signals don't naturally have, they're not naturally complex, but we will see why it is useful to be able to represent signals in a complex way for things like the Fourier transform. Yeah, let's get into it. I'm just gonna move, sorry, the like chat bar was in the way. Okay, ready to go. So at some point in the history of mathematics, dating as far back as like the 14 to 1500s, mathematicians realized a need for a number that gives a negative result when squared, i.e. some number to the power of 2 is equal to a negative result, or -1, let's say. Now, we're probably all quite familiar with real numbers. These are the numbers I've got on the side, got some examples here. They're the numbers you learn when you're learning to count. And basically any number you can think of at this point until we get into imaginary numbers. And if you think about squaring any of these numbers, positive or negative, the result when squared is always going to be a positive real number. So at this point, we can appreciate that any real number squared gives a positive result. You can try squaring 5 squared will equal 25. That gives you a positive result, not what we're looking for. You can try squaring -2, and it will also give you a positive result of 4 because the minuses will cancel out from the squaring. There existed no such number x where x squared equals to -1. So mathematicians decided to invent one, which they called the imaginary unit, I, defined such that I squared is equal to -1, and that I is equal to the square root of -1. In this introduction to complex numbers, I'll use both I and j to refer to the same quantity, the imaginary unit. J is often used instead of I to represent the imaginary unit, as in electronic engineering, I is reserved for current. The invention of imaginary numbers gave way to the possibility of complex numbers. Complex numbers are the numbers that have a real part and an imaginary part. The form in which I've introduced complex numbers is called Cartesian or rectangular form. It has a real part A and an imaginary part BI. We'll now attempt to visualize some complex numbers. To appreciate the use of imaginary and therefore complex numbers, it is useful for us to visualize them on a plane. First, consider the real number line. This is the familiar number line that we've been taught to count on from a young age. The real number line will form our x-axis, which we'll refer to as our real axis. Now we'll place an imaginary number line perpendicular to our real axis. This will be our y-axis, and we'll refer to it as our imaginary axis. This type of diagram is called the complex plane, or sometimes referred to as an Argand diagram. As we previously introduced, a complex number is a combination of a real and an imaginary number and can be visualized on the complex plane as a point. This has coordinates real, imaginary, relative to the origin. The visualization of complex numbers on a complex plane is an important step to understanding complex numbers. We can see here that this complex number Z1 has a real part on the real axis of 4, denoted by the dashed line, and an imaginary part of 3i. Let's plot another complex number, Z of 2. This point has a real part of -2 and an imaginary part of +1i. Finally, let's plot a third. This complex number has a real part of 2 along the real number line and an imaginary part of -4 along the imaginary number line. It's useful to note at this stage that complex numbers can have either a real or imaginary part that is 0. If the real part is 0, then the number will lie on the imaginary axis. Conversely, if the imaginary part is 0, the number will lie on the real axis. As you may know, the values of measured audio signals are not inherently complex. However, representing signals, real signals with complex numbers can be extremely useful at times. We often wish or find it advantageous to break down a signal into a variety of component sinusoids at different frequencies. Hence, complex numbers are significant in signal processing. More on how this works in a later episode when we look at the Fourier transform. For now, just know that when we perform a Fourier transform on a signal, each frequency component in the output has a magnitude and a phase. This is actually a complex number whereby the real part is the magnitude and the imaginary part is the phase. Complex numbers also have a magnitude and a phase, which we'll see in a moment when we begin to visualize them in polar form. Therefore, it comes naturally to use complex numbers to represent the magnitude and phase of sinusoidal components. Again, measured audio signals are not inherently complex valued. However, sometimes it can be really useful to represent these signals with complex numbers. It is often useful to be able to measure the phase of a signal, which may be done easily using trigonometry if the data is represented as complex numbers. Following this, an alternative way to represent complex numbers is by the distance from the origin, which we'll call the magnitude, and denote as r, and the angle from the real positive axis, which we will denote as the Greek letter theta. We can now see that we have a right-angled triangle and that our magnitude r is the hypotenuse. We can now calculate the magnitude with Pythagoras' theorem. Polar form is often represented, as we see on the left here. Z, the complex number Z, is equal to the magnitude r, and this symbol next to r is, in mathematics, an angle symbol. So a magnitude of r and an angle of theta. We can see that on the right angle triangle, we have an adjacent and an opposite, and this will help us calculate the angle theta in a moment. First, we can calculate r with the Pythagorean r equals to the square root of a squared plus b squared. And we can see from our complex number that our a is 4 in this sense, and our b is 3. So let's plug those numbers in and see what we get. We simplify it to the square root of 25, and then we get the answer 5. So our magnitude R is equal to 5. Next, we want to get the angle from the real positive axis of our complex number. We know from trigonometry that tan of theta is opposite over adjacent. But we don't exactly want tan of theta. We want to have theta on its own. So we can do this by taking the inverse tangent or the arc tangent of opposite over adjacent. Let's plug those numbers in and see what we get. Our opposite is 3 and our adjacent is 4. Our angle is in degrees and it's 36.87. We can now represent this in polar form. Oh, I think I was meant to have the answer in polar form there, but in polar form it would be now 5 angle and theta would be 36.87. Okay, so we can actually use the same rules that we do for arithmetic with real numbers with complex numbers. And we can see that there's a few different forms of complex numbers shown on this page. And we're going to look at which forms are best for which kind of calculations. So for simple addition and subtraction, the best form of a complex number is what we call Cartesian or rectangular form, which is the first form of complex numbers that we saw. And you've got this up the top as z equals a plus bi. And I've got a couple of complex numbers here, 5 plus 9i and 4 plus 7i. And if you want to add two complex numbers, all you have to do is separate the real and imaginary parts. And what you're going to do is you're going to add the real parts and add the imaginary parts. And if we plug in the values from these numbers, we can see that if we add these two complex numbers together, we get 9 plus 16i. Similarly with subtraction, we subtract the real parts of the complex number from each other and subtract the imaginary parts of the complex number from each other. If we plug in the values from our two complex numbers in Cartesian form, we're left with 1 plus 2i. Now, in order to multiply and divide complex numbers, we can also do this in Cartesian form, but it's a bit more lengthy and involves the FOIL style of multiplication or division, whereby you're taking the first and then the outers and the inners and the last. And what we could do instead is translate this complex number to polar form, which we just saw. Or alternatively, another form called exponential form, which is made possible by Euler's formula given in the top right-hand corner of the page here. More on that formula in the next slide. And by using polar form or exponential form, multiplication and division of complex numbers is made easy because we can just multiply the magnitudes of the complex number together and add the angle or the phases. And we can see that so these complex numbers up here, they are actually the conversion of the ones I just showed you. I converted them earlier. We can see that if we want to multiply two complex numbers together, we can add the two magnitudes R. So in this case, we've got 10.30 and 8.06. And we multiply them together. And then in the exponent, we add the angles. And we're left with this rather confusing looking number, which in the first half before the E is the resulting magnitude of the multiplication. And in the exponent of the E, we have the complex variable J, and then we have our resulting angle, which is 121.21. Then in terms of division, we can divide the radiuses and subtract the angles. So it's just kind of the other way around. Instead of doing addition on the angles this time, we do subtraction, and then we divide the radiuses. So if we plug those numbers in again, same numbers, we can see that we're left with this resulting complex number in exponential form. 1.28 is the radius, and the angle is 0.69 degrees. Okay, now we're going to look at Euler's theorem, or Euler's formula. And this is another representation of a complex number. And we can start to see cosine and sine, which are familiar functions to us as audio programmers. And what we're going to do is we're going to plug in some numbers, just some arbitrary numbers for x here in Euler's formula, and plot them on the complex plane. So let's start off with 1.5. If we plug in the numbers for cosine and sine of 1.5, we're left with this complex number. Let's plot that on the complex plane. Let's choose another arbitrary number 4. And let's plot that one on the complex plane. Let's choose another number and plug in the values for cosine and sine and plot that complex number on the plane. And let's choose one more. 2.5. And let's plot that on the plane. Now you might see at this point that a pattern is emerging at the points where we've plotted these complex numbers based on Euler's formula. And that is that they are all plotted on a unit circle that has a radius of 1. And this is one of the main points of Euler's formula, that everything you plug in for x here will be a value on this unit radius circle, and the distance around the circle will be denoted by the angle theta. And on the other side of the screen here, I've done a bit of a zoomed in plot to show what I mean. So we can see from Euler's formula that the real part of the complex number is cosine theta, and the imaginary part of the complex number is j sine theta. And that this whole complex number is denoted by the term e to the j theta. And theta is just the independent variable in this case. So it means that whatever the angle of theta is will determine how far around this unit circle this complex point is. Now, if we want to visualize this in terms of rotation, which is important for plotting sine and cosine, I've got some animations in the next slide which should help with that. Here we go. So I want you to imagine that you are in the plane of the slide and you're looking where this eye is looking, down this axis, which is labeled X, but that would be our real axis from what we've just seen. And what's labeled I would be our imaginary axis. So if you're looking down this axis X, and you're within the slide, you wouldn't have depth of field, so you would only see this red dot going up and down. You wouldn't be able to see the black dot rotating, you would only see the red dot going up and down. And that red dot, in terms of an imaginary number line, is oscillating between plus I and minus I. Or in this case, we've got +1 and -1. And you can see it tracing the sine wave, which backs up our theory that we just saw the sine as the imaginary part of the complex number. And you can see that in this animation here. I then made a rotation of this animation so that we can look down the imaginary line. And this time, if we were in the plane of the slide, we could see this blue dot going up and down, oscillating between 1 and -1. And this is tracing a cosine. And that is the real part of our imaginary number when expressed with Euler's formula. So I hope that helps to visualize a bit how the rotation would work as theta increases. You can see the theta increasing as the black dot moves around the circle. Finally, let's introduce complex phasors and real signals. Consider a complex number whose magnitude is 1, as we just saw with Euler's formula, and whose phase angle increases with time. As this complex number has a magnitude of 1, it will characteristically lie on the unit circle, as we previously saw by plotting complex points using Euler's formula. As time t increases, so does the complex phase angle theta. Our complex point traverses around the unit circle in an anti-clockwise direction. This is identical to the rotation we just observed in the animations in the previous slide, but this time we consider a complex number that is a function of time, and therefore the rate at which it rotates on the unit circle is determined by the frequency f. For example, if the frequency f equaled 10 Hertz, the point would rotate around the circle 10 times per second. Now, this is a bit closer to what we introduced in DSP Corner 1 when we spoke about the mathematical representation of cosines and sines. And I've put it here in terms of Euler's formula to see how similar this is to how we represented our cosines and sines when we first looked at them. I've also put at the bottom of the page that you could swap out the 2 pi f, which is our frequency, with this omega, which is our angular frequency, which we also saw in the first DSP corner. So that's just to show that you've got this relationship between 2 pi f and omega, and you could swap them out and they would mean the same thing. The complex exponential in the lower right quadrant of the unit circle is what we call the complex conjugate. This complex exponential has a negative frequency and will rotate clockwise around the unit circle as time increases. We'll discuss how negative frequency relates to the Fourier transform in next month's DSP corner. So I hope you'll join me again next month to discuss that further. Thanks for coming to my talk, and I know that complex numbers and imaginary numbers is a really abstract concept. So if this is your first time seeing these kind of things, then please watch some more videos on it. I'll put some more educational videos in the drop down of the talk when it goes up on YouTube. And please feel free to go through slowly and pause the video and look things up. And yeah, as usual, if you have any questions or concerns, please reach out to me.
Fantastic. Thank you so much, Rachel.
Thank you. Let me stop sharing.
And how can people reach out to you if they have any questions?
So I'm on the Discord.
Awesome.
Yeah.
Rachel
Audio
Lock.
programmer Discord as Rachel Lock.
Yeah.
I am on LinkedIn as Rachel Lock. I am on Twitter as Madame Modular. I think that's it.
Yeah. Great. So Twitter, Madame Modular, LinkedIn, Rachel Lock, a Lock with an E at the end, and on the Audio Programmer Discord as Rachel Lock as well.
Thank you. I hope that was helpful for some people.
Yeah, people found it helpful for sure. And one question that I have, and I know that you aren't really taking questions, so maybe Geraint can chime in if he has any thoughts. I just want to make sure I understand this properly in my head. So normally I think of an audio signal as when you draw it on paper, you're drawing it with an X and Y axis, and you're thinking of it in terms of phase and how and values between plus and -1. So would it be fair to say that the complex plane is the third dimension of that, and that the waves are actually three-dimensional, and the Z plane is just referring to, like, if we could pop a value off of the paper in the third dimension? Is that fair to say, or is it more complicated than that?
So there's actually really good like diagrams or animations that show a third dimensional axis of time coming out, and then you'll get this like kind of spiral or helix shape as that rotation happens and as the real and imaginary part are traced out.
Got it.
So maybe I'll put some links to that kind of animation.
Yeah.
And, do you think that answers it, Geraint?
Yeah, you get the sort of the complex exponentials that you've got like the real value and then the imaginary one, and like time, and it kind of, you see it spiral, and then that's nice and intuitive.
Got it. Awesome. Thank you very much, Rachel. Yes. So as we mentioned before, if you haven't joined the community, what are you waiting for? Join us. You can join us on our Discord. We have over 7,500 members from all around the world, all different levels of experience. And you can join us on theaudioprogrammer.com/community. And with that, we move on to our next talk. We have the very kind Tom Poole, who is the director of JUCE and also part of the Audio Developer Conference team as well. And he's going to be giving an overview of the new features upcoming in JUCE 7, and also going to say a little bit about all of the cool things that are coming up for ADC. And with that, I will hand over the mic to Tom. Take it away.
Yeah, thanks, Josh. So yeah, before we sort of dive into an overview of the main features of JUCE 7, it's kind of important that we take a few minutes to talk about the Audio Developer Conference, because we are, well, a couple of weeks ago, we opened our talk submissions platform. And if you're interested in giving a talk, there's only a couple of weeks left for you to do that. The actual conference itself takes place between the 14th and 16th of November, in person in London, but also online as well. And given this audience is already sort of tuned into watching talks about audio, I won't preach to the converted about how much like fun and useful it is. But the submissions is the pressing thing. So if you were thinking of being part of this year's ADC, now is your chance. If you've not given a talk before, or your area of work or what you're doing or your background is atypical, we'd particularly welcome your contribution. Once we've collected all the submissions from everybody, the talks are ranked by public anonymized voting. So if your talk sounds interesting, or whatever it may be, it can become part of the ADC program. Talks are 50 minutes. We have plenty of examples from previous years on our YouTube channel, so you can just look out for free. And if you want to find out more about any of that, the website is audio.dev. So go there, find out a bit more about the program, and submit a talk. So switching.
Yeah. Oh, sorry. I was just going to interrupt and say I'm going to put the link in the chat as well. So it's audio.dev for everybody. And as Tom was saying, if you've never given a talk on audio development before, and you're looking for ways to get exposure into the industry or show people your perspectives on audio programming, I don't think that I can think of a better place to do this other than the Audio Developer Conference. Some of the leading developers and leading people in the industry are there. It's been a huge influence in my career, and I think it's an essential place to go if you want to get serious about audio development, and meet and network with other people who are interested in these things as well. So even if you're not sure if your proposal or your idea for a talk is ready yet, don't be scared to submit to the page, and it's a great opportunity for growth, and I can't say enough great things about it. So be sure to check it out. If you haven't bought a ticket yet, I encourage you to do so. I'll see you in November.
That is a little difficult at the moment.
Yeah. Oh, the tickets are on sale. Yeah.
But yes, please, when tickets do go on sale, that'd be wonderful. And if you wanted to say meet the JUCE team, we're always there, and everyone is very welcome to head over to the JUCE bits and say hello.
Yeah.
So back on JUCE, we could talk about things like upcoming features of the framework, and we've committed to a few recently. So on release, JUCE 7 will contain support for the Audio Random Access SDK, which I'll refer to from now on as ARA, the LV2 plugin format, both hosting and authoring LV2 plugins, new graphical rendering modes on macOS and iOS, and hardware synced rendering on Windows, macOS, and iOS. Coming a little later, but still part of JUCE 7, but not part of the initial release. So this would be something like JUCE 7.1 or maybe 7.2, is MIDI 2 support, more accessibility improvements, and a revamp of our animation clutches, which will tie in to the new hardware synced drawing. We're also hoping to be able to make creating AAX plugins much easier. We've had some really positive discussions with Avid about this, but at least at the moment, we can't commit to saying much more, or even if something along those lines would be part of JUCE 7, but things are in motion. If you were at last year's ADC, or the talk has gone up on the YouTube channel, there is a talk from Avid where you can sort of get a sense of what that might be. Things are in motion. So the ARA support presents plugins with a much more sophisticated API where they can read audio samples outside of the normal time constraints of real-time audio. And when you're not tied to the playhead and a fixed sequence of buffers that come with it, plugins can operate more like sample editors. The poster child for this is Celemony's Melodyne, which, if you haven't seen it in action yourself, allows you to sort of jump around in time and fix audio like you were editing MIDI. It's very impressive, and with ARA support in JUCE, you can create plugins that do similar kinds of things. It's a really rich interface. It's quite a complicated interface. If you're just getting started out with JUCE, then try a normal plugin first. There's really quite a lot going on here, but it is extremely powerful, and we're quite excited to see what people can do with it. LV2 plugin supports. This is really useful because as an LV2 author or host, you get access to a wider variety of platforms and different communities. This has particular impact in open source circles and projects where so the only thing that could be considered is strict open source. And as JUCE is an open source GPL framework ourselves, this is something we want to help support. Rendering improvements are also included in the initial JUCE 7 release. So on macOS and iOS, we have a new default. We've had an asynchronous drawing mode hidden behind a feature flag for those people who are interested in it for years, at least 1 year. So that's had a lot of testing. We've weathered a lot of use cases, and that is now going to become the new default. And the potential performance gains are really quite substantial. We have also fixed our option to force Apple devices to not consolidate disparate rendering regions. So years ago, back in macOS 10, 12 or something, plus or minus one or two versions, you could ask macOS for the list of dirty recs when you came to do your drawing. Now this is really helpful if you have, like comes up every now and then in plugin GUIs, you have some input meters on your left and some output meters on your right. And if both of those change simultaneously, the consolidated dirty rec that Apple sends back to you might be the entirety of your GUI, even though only two little bits at the edge have changed. The Apple does have an API that lets you query this, but it's been broken since that old version of macOS. With JUCE 7, we've made that work again by rendering into our own metal layer and taking like really full control over how updates get presented to the screen. So if you have a GUI that is currently redrawing much bigger areas than it needs to, then re-enabling this option might be a really dramatic change for the better. It's very sort of application dependent. It really depends exactly what your GUI is doing, and you'll want to try this out. The other rendering related change is hardware synced drawing. So now GUI invalidation regions are batched and drawing commands are only issued when the screen will actually be updated. This gives us automatic support for Apple's ProMotion displays that feature like an adaptive display rate. And on Windows in particular, this eases pressure on the main GUI thread. Before JUCE 7, you can get into situations where the main message thread was flooded with messages about tiny invalidation regions, like tens of thousands of them in the worst case. But now we're bringing that back down to a single message at the rate of which your display or displays are refreshing. And then this means that your whole application isn't bogged down. We plan to do this for Linux and Android too, but it's just Windows, macOS, iOS for the initial release. MIDI 2 is coming. If you dig around the JUCE code base at the moment, you'll see that we have an internal MIDI 2 API that we haven't yet exposed to the public. We've been waiting for a few things. So one is platform support. Apple has published their MIDI 2 API, and much more recently, so has Google in Android. We are, because we want to support all of them, it would be really nice to know what Microsoft requires us to do before we put out an API that might be incompatible with their particular dance. And we'd also like some devices. There are a few around, but with some help from the MIDI Association, we're going to get some test hardware pretty soon. So although we're not in direct control of both of those factors, we are confident enough that Over the course of JUCE 7, we will have resolved both of those, and we'll be able to sort of publish our MIDI2 API. Accessibility. JUCE 6 introduced an entirely new accessibility framework within JUCE. And since then, we've had several of our larger customers adopt it. And what's really nice about large customers is they have huge testing facilities and access to many more people than we can reach. So we have lots of really excellent feedback from all of that. And we're committed to implementing like the most important new feature requests off the back of that in JUCE 7. So accessibility will keep getting better. And the last thing I mentioned was a revamp of our animation classes. With the introduction of hardware synced drawing, we can plumb those screen refresh changes up to our users. And this will mean that user created animations can run much more efficiently. In the sense that this will be like working with OpenGL, where you get a callback where you need to provide new content. And this means that you can do a minimal amount of drawing whilst also updating every frame that you need to. So that's it. That was a very quick blast through the headline features. And I think we now have a time for a few questions.
Great. Thanks for that, Tom. Leon Skeptic asks, is there any Visual Studio Code exporter yet for the producer? Assuming that you'd probably have to use CMake for that. Am I right in saying that?
We don't have a Visual Studio Code exporter, but as Josh said, we do support CMake, and there is at least one very well supported CMake integration in VS Code. So that would be the way to go there.
Great. What about clap support? Is that up and coming in JUCE?
We have no immediate plans to support clap. There's plenty of discussions about it, but at the moment, clap support doesn't actually buy our users anything that they can't get with the other plugin formats. So the sticking point here seems to be, if you're a plugin manufacturer, and most of our users are, you need to support Cubase, so you have a VST3. You need to support Logic, so you have an AU, and now we have LV2 for like all the rest. And between those, you get complete DAW coverage. So if we throw clap into the mix, you can also have a clap version of your plugin, but it's extra complexity for no more addressable market. Maybe things will change. So I'm really personally supportive of the clap movement. I think it's a very good thing to get going. But at the moment, for JUCE users, I just go on the forum and look at the most requested things or the top voted feature requests. There's much more clamoring for us to be working on them rather than clap. So it might take a while for it to sort of bubble up in importance.
Great. At Sushi asks, when will you go for web or WebAssembly? Is that in development for JUCE?
It's something we think about a lot. I think that is probably the future of JUCE. So it isn't me committing to anything, but the way we would do that is that last year it was possible to get a web view in Windows that was as capable as all of the other platforms, and that was kind of what was holding us back. And we're now in a position where if we're using the modern web views on all of the platforms, then it is really feasible to write a GUI using HTML, JavaScript, all your lovely web technologies, and have some kind of hook in the back of that where your JavaScript could talk to C++. There's at least one video by the folk at Output who've tried this approach with JUCE, just with their own functionality built on top of it. and that appears to be working well for them. So yeah, this is something we would consider putting into JUCE directly.
Great. What about GPU processing support? So you have OpenGL. What about Metal or Vulkan?
So this is difficult. I think the future may be web GPU and a wrapper that sits on top of all platforms. So the problem with so JUCE's sort of main selling point is that you write code once and it runs everywhere. If you write some Metal code, that is only going to work on Apple devices. If you write some Vulkan code, it's not going to work on most Windows computers because the driver support just isn't there yet. Like it's not going to be reliable enough that you can just run Vulkan and it will work everywhere. And Apple's a pain. There's some sort of adapter layers that you can add to your app, but it sounds nice in principle. If you actually try to use them, they're a real headache. So that leaves a few things. There's 2 projects from Google. One is Angle, which lets you write GL. Not sure of the exact version, but the one that's most common in web browsers. And that translates that into native calls on each platform. So you write to that specific version of OpenGL, and that will be translated into Metal on Apple devices, for example. Or we work towards web GPU. And again, Google has a framework called Dawn, which does the same for web GPU commands. It translates them into the native GPU on each platform. We're still looking at both of those.
Great. Another question, what about Wayland support?
That's on our to-do list, yes.
What's Wayland?
The successor to X. It's a sort of GUI manager for primarily Linux.
Got it. Great. That looks like all of our questions. Yes, that's all of our questions. Thank you very much, Tom. Yes. And before we go, just another quick shout out to the Audio Developer Conference. If you haven't submitted a talk and you're considering doing a talk, be sure to submit. What are you waiting for? You can go to audio.dev to submit. And with that, we can wrap things up. Geraint, Rachel, and Tom, thank you very much for your presentations. Really awesome. And anybody have anything they'd like to say before we sign off?
I just tried to post the diagram of the complex phaser rotating about the time axis in the chat, but I think it flags links as spam, so I'll pop that in the Discord.
Yes, and if you want to send that to me directly, I'll put it in the video description as well.
Perfect.
Cool. And with that, thank you very much to everybody who's joined us this month. And I have this bad habit where I always forget to look at what the date next month is. I think it's the 12th of July. It is indeed the 12th of July. So we will be back here again, the 12th of July. So we're here every second Tuesday of the month. And yeah, thanks for joining us. And if you have any talks that you'd like to propose for any of our meetups, you can do so if you go on over to theaudioprogrammer.com/submit. Then you'll be able to submit a proposal for the Audio Programmer Meetup. And this is a great way to get started if you're feeling that you're not quite ready for ADC yet, and you want a nice gateway to move on up to the big show. We're happy to support you. If you're a student that's looking to present your ideas for the first time, we welcome you. And also if you're experienced in the industry like these 3 folks, then we welcome you to do that as well. So yes, and with that, we will sign off. Thank you once again to everybody who joined us, and we will see you next month. Cool. And we're off. Thank you very much.